Welcome back. Problem 11-22. So statement is determine the minimum depth h of the beam to the nearest 1/8 inch that will safely support the loading shown. The allowable bending stress is 21 ksi and allowable shearing stress is 10 ksi. The beam has a uniform thickness of 3 inch. So you can see this is an overhanging beam, clear, having uniformly distributed load from B till end, that is 4 kips per feet, and there is a rolling support at B and pin support at A. So thickness of this beam is rectangular, so this thickness is 3 inch, clear. So you have to find this height h, minimum depth h. So let's start with the solution. So first step, you can see that this load is downward, clear, uniformly distributed load. So if we remove this support, this force will be upward and this reaction force will be downward. So if we remove this support, so we will having a reaction force which will be equal to RB, and if you remove this pin support, so you will be having a reaction force which is equal to RA. So we'll first find this RA and RB by using equilibrium condition. So first equilibrium condition is that sum of all moment about point B is equal to 0 and taking the counterclockwise moment as positive. So about point B, the first moment will be due to this distributed load when converted into point load. So it will be 4 into 6 and that will be acting at 3 feet. And this is producing clockwise, so it will be negative. The second moment will be RA into perpendicular distance is 12 feet and this is producing counterclockwise. Their sum must be equal to 0. So I will first convert this distributed load into point load. So 4 into 6 and that will be acting at a half. So this will be 3 feet. Clear? So I will write 4 into 6 multiplied by 3, that is producing clockwise, so it will be negative, plus RA into perpendicular distance is 12 and that is producing counterclockwise, so it will be 0. Their sum must be equal to 0. So 12 RA is equal to 4 into 6 multiplied by 3. So when you calculate it, you will get RA will be equal to 6 kip. Clear? R will be 6 kip. RA will be equal to 6 kip. Now we'll find RB by using this equilibrium condition that sum of all forces along y direction must be equal to 0 and upward force is positive. So RA is downward, so minus RA which is equal to minus 6 plus RB which is upward minus 4 into 6 because this is downward is equal to 0. So RB minus 30 is equal to 0. So RB will be equal to 30 kip. Now you have both RA and RB. So we will move further. We know that allowable bending stress is equal to maximum bending moment into C divided by I, or you can see that this will be also equal to maximum bending moment divided by I divided by C. So this I divided by C is section modulus, so we can see that allowable bending stress is maximum bending moment divided by required section modulus. Clear? I will write it S is equal to I divided by C. So we have been given this is a rectangular in cross section, clear? So this thickness is given as 3 inch, sorry, and this is the height which we will find, h. So required section modulus is equal to I divided by C. So if I draw the horizontal line, clear? So distance from neutral axis till topmost, this is C which is equal to h by 2. Clear? And moment of inertia I for this rectangular beam is equal to 1/12 BH cube. So B is 3 and H is not known, so H cube. So we will get 3H cube over 12 which is equal to H cube over 4. This is I. and C is equal to h by 2. So what if I put it over here? So we will get required section modulus is h cube over 3 divided by h over 2. So we will get h required section modulus will be equal to h square over 2, which is equal to 0.5 h square. So we have required section modulus clear. So we do not have this maximum bending moment that we will get from shear force and bending moment diagram. So for that I will draw a vertical line from the end of the beam in order to find the shear force, maximum shear force and bending moment. So first there is a horizontal line to show x in feet. We have on y-axis we have shear force that will be in kip. So let each division is of let's say you can see that is 5 kips. So 5, 10, 15, 20. I do not have the space, so I will change it. So this will be, let this is 10 kips. You can adjust as per your requirement, 30 and 40. Similarly, minus 10, minus 20 and so on. So first point at this is RA, which is downward. So it will be, this is minus 6. So I will locate first minus 6. So let this is minus 6. Now moving from point A till point B, there is no other force, so it will remain same till this point. So I will draw a line at this. Now at this point you have RB, which is 30. So minus 6 plus 30 will bring it to 24 plus 24. So first we will locate point 24. So 24 will be somewhere here. So shear force will change from this to 24. This is 24 kips. This is minus 6 kips. Now here you can see there is a uniformly distributed load. So at this end, this total load will be equal to 4 into 6, 24. So plus 24, this load will be 4 into minus 4 into 6 because that is downward, so minus 24. So plus 24 minus 24 will bring it to 0 at this point. And you can see that this uniformly distributed load is a horizontal line with 0 degrees, so bending moment will be 1 degree higher and slope will be decreasing because these are downward. So I will get the shear force diagram will be like this. Now we will move toward bending moment diagram. So for bending moment diagram, again I will draw a horizontal line. X will be in feet, clear, and here you will be having bending moment that will be kips into feet. So let each division is of 20. So minus 20, minus 40, minus 60, minus 80. The first area bending moment at this point will be 0 because x is equal to 0. So first moment under the first area under the shear force diagram is this one, and this one will be equal to minus 6 into length, which is 12, which is minus 72. So at this point we will have minus 72. So first we will locate the point. So minus 72 will be somewhere here, kips into feet. Now you can see that shear force is a horizontal line with 0 degree and this is negative area. So bending moment will be 1 degree higher and slope will be decreasing. So we will join them using a straight line. So this will be our first. Now the second area under the shear force diagram is this area, and this area you can see this is a triangular. So 1 over 2 into its height, which is 24, and length is 6 feet, and that will be equal to plus 72. So minus 72 plus 72 will bring it to 0. So this point, and since this line is a this is a 1 degree line and slope is decreasing, so bending moment will be 1 degree higher. It will be a second degree curve, and this will be slope will be increasing because this area is positive area. So this is your bending moment diagram, BMD. Now from this BMD, I will write from bending moment diagram, you have absolute maximum bending stress, bending moment, maximum absolute value of bending moment is minus 72, which will be equal to 72 kips into feet. So this will be your maximum absolute value of bending moment. So you have now bending moment as well. You have the required section modulus. So just put it in this formula, required section modulus. We know that allowable bending stress is equal to maximum bending moment divided by section modulus required. So section modulus will be equal to maximum bending moment divided by allowable stress. Required section modulus is 0.5 h square. Maximum bending moment is 72 kips into feet, so we convert it into inch. So we will multiply by 12. Divide by allowable bending stress, which is equal to 12 ksi. So 12 into, not 12, allow 21. This is 21, okay. So 21. So from here you will get h square is equal to 72 into 12 divided by 21 multiplied by 0.5. So when you take the square root of this, you will get h is equal to 9.07 inch. Since we can write it 9 plus 0.7, and we have been given that h should be near 1 over 8 inch. So 1 over 8 inch is equal to 0.125 inch. So instead of h is 9.07, we will write h is equal to 9.125 or 9 plus 1 over 8. So h will be your answer. We will use h is 1 by 8 inch. So this is the answer. Now we will counter check it with the shear force. So for counter check, I will write for checking, we'll check it with allowable shearing stress is equal to V max into Q max divided by I into T. So V max from shear force diagram, you will get V max is equal to 24 KSI. Let me show you. You can see the maximum stress is 24 KSI. And I is again equal to, which we have calculated over here, I was h cube over 4. So h cube over 4, and h is 9.125 inch. Clear? Cube divided by 4. Clear? And that will give you 189.95 inch power 4. Thickness is given as 3 inch. You can see here this thickness of this beam is 3 inch. So only thing we have to find is Q max. So let me draw the cross section again. This is 3 inch, and now height is 9. H is equal to 9.125 inch. So if you draw the neutral axis that will lie at the half of this, so we will be having this portion will be equal to h by 2. Clear? So h by 2, which means 9.125 divided by 2. So what will be the Q max for this portion? So Q max is, we know that Q max is equal to Y dash into A. So what will be the Y dash? So Y dash will be the mid of this. This will be the Y dash from the neutral axis. And you can see this is Y dash bar. And that will be equal to H by 2 divided by 2, which is equal to Y dash will be equal to H by 4. So H by 4 into area. Area of this cross section is equal to 3 into H. 3 into H by 2. So I will write 3 into H by 2. So H is 9.125 divided by 4 multiply by 3 multiply by 9.125 divided by 2. So when you calculate, you will get Q max will be equal to 31.22 in cubic inch. Now you have all the values in this formula, so you can just put it over here. I will write it again. Tau allowable is equal to V max into Q max divided by I into T. We can also say this is the maximum shear stress developed due to this height h and given loading. So maximum shearing stress given, we are finding it, V max is 24 ksi. This is the V max. This is I and this is Q and this is T. So V max is 24 ksi, so 24, and Q max is 31.22 divided by I, which is 189.95, and thickness is 3. So when you calculate it, you will get maximum shearing stress comes out to be 1.315 ksi. So you can see this maximum shearing stress is less than given allowable shearing stress in the question, which is 10 ksi. So this is 1.315 is less than 10 ksi here. So the end result is that hence the minimum depth H of the beam is 9.125 inch. And that was all about this problem 11-22. I hope you have enjoyed this video. Those who are new to my channel, then subscribe it and press the bell icon so that you can get notification about any latest video which I post. And if you have any question, you can ask me in comment section. Thank you for watching.